Electrical machine design, transformer winding, design of LV winding. Man engineer welcomes you all. EMD, electrical machine design. In this video, we see design of LV winding, how to winding, how to design steps in this video. Same steps for design of LV winding in this video. Seen. Kindly use this video. Design of LV winding. Number of turns per phase T to S equal to V2 divided by ET, where V2 is voltage rating of LV winding per phase. ET is EMF per turn. Note, first point, the number of turns per phase should be rounded off to the nearest minimum integer. Second, 50% of turn accommodated at each limb for quarter transformer. Step 2, area of cross section of conductor A to S I2 divided by del 2, where I2, current rating of LV winding, kVA for phase into 10 power 3 bar V2. Del 2 is current density in LV winding, 1.8 to 2.3 ampere per millimeter square for distribution type transformer. Del 2 value 2.1 to 2.3 ampere per millimeter square for power transformer. Note 1. Cylindrical winding with rectangular conductor were used for LV winding and also for HV winding of large transformers. Note 2. If area is more than 50 millimeters square, kindly note is more than 50 millimeters square, standard conductors are used. Standard conductors to be transposed to equalize the reactance of strands. Note 3. The dimensions of rectangular conductor in a direction perpendicular to the leakage perpendicular to the leakage flux line should not exceed 3.5 mm. Step 3. Dimensions of conductor HW winding height is equal to 80% of HW. HW is winding height. Capital HW is winding height. Remaining 20% of axial insulation. Axial insulation. Step 4. Standard size of strand is equal to axial length into radial width. Step 5. Standard size of a strand in width insulation. Axial length plus insulation into radial width plus insulation. Bracket is very important. Step 6. Axial length of a conductor is equal to number of strands into axial length of each strands. Therefore, number of turns axially for on each limb. Therefore, number of turns axially on each limb, that is winding height divided by axial length of conductor. Design of LV winding. Radial adjustment of LV winding. Radial thickness of insulated strand of LV conductor. Second, radial width of the conductor is equal to bracket of number of strands into radial thickness bracket. Note, for a double layer radial winding, the two layers are separated by an in separated by an insulation cylinder of 0.5 to 1 m thickness. Therefore, the radial width of LV winding. B2 formula is equal to radial thickness of first layer plus thickness of an insulation cylinder plus radial thickness of second layer. Third step, radial adjustment of LV binding. Inner diameter of insulation cylinder is equal to small g. Fourth step, thickness of insulating cylinder is Ti. Outer diameter of insulating cylinder di naught is equal to d plus 2 ti. Sixth, radial adjustment of LV point. Sixth point, oil duct between insulating cylinder and LV binding is equal to T naught. Radial adjustment of LV binding. Seventh point, inner diameter of LV binding di2, capital di2 is equal to small di naught plus 2 T naught. Radial adjustment of LV binding. 8th point is radial width of LV binding B2 calculated already. Ninth point, outer diameter of LV binding capital D02 is equal to DI2 plus 2B2. Mean length of turn. First point, mean diameter of LV binding. dm2 is equal to di2 plus do2 divided by 2. Second point, mean length of turn. Mean length of LV turn LMT2 is pi dm2. Resistance of LV winding. R2S, small R2S, rho LMT2 T2 divided by A2. Fourth point, copper losses for LV winding. I2 squared into R2. Next video we see problem of design of LV winding. That is 15 marks problem. Kindly see it and use this next video and in that video. Man engineering, thank you.